Hey guys, my name is Adrienne and welcome to Organic Chemistry 2, Part 4 of these recorded sessions. So today we'll be going over for most of y'all Chapter 16 and in general Conjugation, Resonance, and Dienes. And as you might have figured out watching the last videos, hopefully, and compared to OChem 1, this is a different format. We'll be doing study questions. And the reason why I did this is because OChem 2 is a lot of practice questions, just practice questions, and a lot more complicated reactions that will take up too much time to draw out or, graphs and charts and things like that. So it'll be easier this way. And also because, again, it's just a lot of practice questions. And we will still have the summary at the end. So you can always skip to that part if you want to see how I summarize the chapter, what are the relevant topics, or if you just really need practice, the 20 questions per video is really important, is really great, right? And trust me when I say this is these questions, same for all the other videos, are really important, really signifies signifies the questions that you'll be asked on your exams, things like that. So, with that being said, let's get started with the first set of questions from the review. Okay, so again, you can pause, take notes. I encourage you to take notes, try and answer them, and then, you know, it doesn't hurt to try, right? And for the most part, you guys should have already, been going over these chapters, things like that. So, it shouldn't be too bad. And as always, they're always chronological, so you can follow along with your chapter, so you don't have to keep flipping back and forth pages, right? Things like that. So give, I'll give you a couple minutes to pause the video and see what you got. Okay, so for one, you guys should have gotten C, and this is just one of those things like they ask you just cause it's nothing too complicated. It's literally just a definition, right? C, 1 and 3, those are the conjugated because we see that those double bonds are every other one, right? So this is one of those things like, oh, let's see if you know what conjugated means. 2, you should have gone B. And this one, resonance, right? We know resonance from OChem 1. We know resonance from, several reactions throughout OChem 1. And now it's making a comeback because resonance is pretty much conjugation, right? And we'll see later how it's different. Um, but for now, what's true about resonance structures? Only the placement of pi bonds are different, right? So pi bonds only. We don't care about the atoms, the sigma bonds, or non-bonded electrons. So pi bonds, um, delocalize, right? That's the key word, delocalize. Pi bonds delocalize. So 3, and again, this one's kind of a throwback from hybridization, right? Back in OChem 1, and they always come back because there's always like it's not exceptions, it's just like review, like make sure you know this, make sure you review this and make sure you don't forget about this because it's not always going to be common, right? So for this instance, 3, you should have gotten B. And why is that? From what we learned about sp3 minus number of pi bonds, right? That was our like shortcut formula for hybridization, right? And this structure doesn't have any um, pi bonds. So how is it, or I guess this oxygen, right? This oxygen doesn't have any pi bonds. So how is it sp2 if it doesn't have any pi bonds, right? This formula doesn't make sense now. Well, we know lone pairs affect geometry, right? And in this case, it has an extra lone pair than it than normal, than neutral form, right? So you count one of those lone pairs as the pi bond, right? Because one of these lone pairs, let's see, I'm gonna color it in. So you just take one of these lone pairs, and we know because it's just 1 to 1, right? So one of these must be in the p orbital, right? And that's how you get sp2 because one of these is in the p orbital, so that means it counts as a pi bond, right? A pi bond, but it's not technically, but it's still in the pi position, the p orbital. So that's how you do that. Lone pairs, especially lone pairs. Let me write this down. Lone pairs count as pi when there's extra, right? Like in this case, there's an ion, right? When, or I should say, an ion, right? The extra charge and things like that. And you'll see that more later as well, with more examples, not just oxygen but other things. So, and as long as you understand this p orbital, we it's been a while since we went through the little details of hybridization, things like that. But once you get think about it, it makes sense, right? P orbitals are pi bonds. Okay, so let me change the color, right? Okay, so for 4, which of the following is conjugated? Again, this is like the same as 1, right? You should have gone D, right? And we know D because again, other there's every other double bond, right? So let's see, let me just draw this over here, and even here, right? So conjugation is pretty much like resonance, right? Um, with a few exceptions, but for the most part, you can think of it that way. Anyways, I think of it that way. Conjugation resonance are go hand in hand. But yeah, this pi bond can move over here, then this pi bond can move over here, and this carbocation can move over here, and then this pi bond can move over here, and vice versa, right? Just keeps moving. But again, in this instant, it's resonance. It's fully conjugated, I should say. But it doesn't always have to be fully conjugated to be a conjugation, right? It can just be, again, this one is conjugated, but it's not like a cyclic or anything, right? So, okay, 5, you guys should have gone, again, heat of hydrogenation. It's been a while, but you guys should have gone, um, in this instance, D, right? So why D? Well, in this case, heat of hydrogenation does what? So heat of hydrogenation increases as stability decreases, right? So pretty much think of it as energy. We know 3 is the least, or it's not even conjugated at all, right? It's the least stable out of 1 and 2. So the takeaway from this is that conjugation stabilizes, right? Now, you might be thinking, so what's the difference between 1 and 2, right? What's the difference between 1 and 2? Well, you can kind of see for 1 and 2, 1 is less stable because it doesn't have as many conjugation as 2, right? So 1 is this, and then 2 is this, right? These end up in the terminal, right? So this would make like anion, things like that, if they were to move over here, and then they can move to this way, which is no problem. But in this case, we won't have any charges if we conjugate this way, right? It's still going to be double bond, a pi bond, or the other way, right? So 2 has no charges, and we know charges mess up stability, right? And we know that from like carbocations, things like that, carbocation stability. Um, yeah, so we know charges, even in resonance, right? We know resonance, the more charges it has, the less stable the resonance structure is, right? So things like that. So 2 is more stable, aka um, the the one that has the lowest heat of hydrogenation. So again, just think of this, and I know heat of hydrogenation is not really just think of it, heat hydrogenation is pretty much just energy. So we know the less stable something is, the more energy it has, right? Okay, so that's that for this page. Hopefully all went well. Hopefully the explanations helped you guys. Then again, feel free to just screenshot these. If you want to do it on your own time, feel free. And again, this next page, screenshot it, save it, take notes, do whatever, pause the video so you can follow along, things like that. So yeah, I'll give you guys a minute or two. Okay, so 6, what is the reactive intermediate of the reaction between 1,3-diene with HBr resulting in 1,4 addition? So 6, now we're getting into reactions, right? You guys should have gotten D. And why is that? So the reactive intermediate in the reaction of 1,3-diene, this is our 1,3-diene, plus HBr, resulting in a 1,4 addition. Right, so 1,4 addition, we should have something like this. Br, right? So that's our product. So that's our product. So what in this type of reaction, 1,4 addition, what is the intermediate, right? So we know addition reactions cause um, what kind of, I guess, ion? A carbocation, right? Because once you add something, it'll take away a pi bond, and then one of those pi bonds, right, or one of those carbons in the pi bond is now missing a bond, so now it's um, a carbocation, right? And that's how you come up with D, because this is basically what it looks like, right? Especially for 1,4 addition, and we know 1,4 addition is one of the additions from conjugation, and there's also the 1,2 addition, right? But in either case, they're both additions, and they both cause carbocations because that's where you add the halogen, right? So our intermediate would look something like this, right? So allylic carbocation. So nothing too crazy. It's just as long as you know what addition reaction does, you could have gathered it was a carbocation. And also we know we don't work with radicals. We've never have bromonium ion. It's not even a cyclic, right? So that would make sense. How would we get cyclic from just addition? A unifile, maybe, but where's the Br going to add if it's just a diunifile? Because diunifile is just double bond, right? So allylic carbocation, the best bet. And allylic, our structure is literally allylic, right? Okay, so 7, you guys should have gone B, right? 2 and 4, following reaction. So the thing about this one is that um, it's also, again, addition reaction. So now we're talking about 1,2 and 1,4 addition, right? So which one is which? Or I guess 2 is a what addition? 2 is a 1,2 addition, so I'll put that over here, and then 4 is the 1,4 addition, right? and it makes sense. So the thing with addition reactions, so let me just draw this. We don't really care about anything but the diene. So we have this. This is what we're given, right? So we don't really care about the rest of this. We just care about the diene, right? The four. So we could have we could as long as we have this, right? We're good. And we know that hydrogen hydrogen always at the first carbon at first carbon. So we could have gone from this way or this way, right? So either way, it's okay as long as H is either here or here, and then Br is two position or in the four position, right? So this is pretty much the takeaway from this. H is always the first carbon cation because you see at choice one and choice three, they kind of like flip flopped, right? So H always goes to the first carbon no matter what. Okay, now 8 is kind of the same, but this time instead of hydrogen, we got DCl. So we know D is a what? D is just another derivative of hydrogen. It's deuterium, so it's like H hydrogen but larger, right? And again, this is another 1,2,1,4 reaction, and this one is actually simpler because we don't have any intermediate or I mean substituents on our reactant, right? So for 8, you guys should have gotten C, 1 and 2, and again, the H derivative is always with the first carbon, right? So this time it's the D. So 1 is actually our um, 1,2 addition, right? While 2 is our 1,4 addition. So, and you can kind of tell, right? For here, it's pretty much the same as the other one. And again, we can number it from either ends, right? So we could start here as 1, 2, 3, 4, or we could start here as 1, 2, 3, 4. So our H could be here, or the 1, 2 addition, and our Br could be here, right? And vice versa. You can, again, number it from either ends, right? So that's kind of best thing about 1, 2, and 1, 4, as long as we just care about these four carbons pretty much. We're not doing anything with this side, right? We don't care about this side. We just care about these four, and that's all you got. And how do we know when we make or when we go through 1, 2, and 1, 4 addition? Well, we know we do that because again, this is it's conjugated, right? So it's important to know, it's important to find out if the thing is conjugated, because if it's conjugated, you'll go through a 1, 2, 1, 4 addition, right? Because they're conjugating, and that's all there is to it. Okay, so now 9 is pretty much the same questions, but now it's asking in a different type of way because we know 1, 2, and 1, 4 addition are either kinetic and thermodynamic, right? So 9, you guys should have gotten B because thermodynamic. Thermo is what addition? 1,4 addition, right? And ob- obtained from the addition of HBr to 1,3-butadiene. 1,3-butadiene plus HBr. And said thermo, so our product again is just like that, right? And that's 1 bromo, 2 butadiene. So this is our 1, 2, 3, 4, right? So not too bad. And then 10, which of the following statements about kinetic versus thermodynamic products is true? So we kind of just talked about it. 10, you guys should have gotten B because kinetic product predominates at lower temperatures. So we know thermo is obviously going to be the hotter temperature, right? Thermo. Um, high temp slow, and then kinetic is obviously the fast one. Low temp, fast, right? So nothing too bad. Um, and actually going to, let's see, C should be what C is one of the iffy ones. So for C, the product part that predominates at equilibrium is kinetic product. So why is it not true? Because thermodynamic is the one that predominates at equilibrium because it's more stable, less stable, right? So this thermo predominates at a more um, at the equilibrium because it's more stable, right? So that's all there's to it, and yeah. So think of these are this is pretty much a summary of thermo and kinetic products. So that's good. Okay, so let's move on to the next page. Okay, so again, pause the video, take a couple minutes, and see what you guys got. Okay, you guys still here? Okay, 11. You guys should have gotten what is it? A, right? So not a feature of Diels-Alder. For sure, we're gonna make pi bonds. We're gonna break pi bonds. We're gonna form new six-membered rings, right? And they are considered, aka, one step, right? So peroxides, they don't do anything with peroxides. Um, as long as they have diene, dienophile, we're good, right? Okay. So now for 12, which of the following is least reactive diene in Diels-Alder? So for 12, you guys should have gone D and YD. So for Diels-Alder, we need, what kind of diene do we need? An S-cis diene, right? S-cis diene. So, of course, these are drawn in a way that they're not S-cis, but we can rotate them because S-cis just means rotating the double bonds um, from that from the single bond between them, right? So for one, for example, so let me see. For one, for example, you should look something like this if once you twist it, right? And then two, like that, and you're kind of starting to see like why things are more or less stable, right? And then this one, right? So our that's all S cis, right? And S cis is just this is the S, right? This is the S and this is the cis. The double bonds are cis. The double bonds are cis. Double bonds are cis. Double bonds are cis, right? So we just rotated it around that single bond. So now, just looking at this, which one's the least reactive? You can kind of tell right away, right? Which one's the most hindered, the most kind of subjected to like closing, or I guess hindrance, steric hindrance, things like that. And you can kind of see here, if we were to have a Diels-Alder reaction, the bonds would go this way, right? Right, the bonds would make over there. Because again, we're making a six-membered ring. But in this case, there's already a bond over here. So where are the new bonds going, right? You can't have a bond going outwards like this and make a weird looking six-membered ring, right? So that's why it's D. It's just the less, the more hindered and the more kind of awkward things like that. And that just goes with stability. That just goes with hindrance, right? I said hindrance way too many times. Hindrance. Okay. So now 13. 13, I'm probably gonna say hindrance a lot again. Actually, no. Actually, no. We'll wait on that. Let's see. So rank the following in order of increasing reactivity in Diels-Alder. So 13, pretty again, um, straightforward. And 13, you guys should have gone B, right? And again, that's just with hindrance, things like that. So for B, 3, and then 1 and 2, right? And this one's a good one, actually, because again, um, well, I guess not again because we haven't mentioned it, but this is actually not about hindrance, and you can see 3, the most unhindered, is the least reactive. And why is that? So, electron withdrawing groups increase reactivity. So, increase electron withdrawing groups, obviously, groups that are electronegative and they take away your electrons, right? They pull electrons away from the double bond. And 2 has 2 carboxylic acids, and just by looking at it, it has a lot more oxygens, right? Those oxygens are pulling everything from it, I guess, towards it, right? Pulling everything towards it. So the more electron withdrawing groups you have, the increasing reactivity. So this is a good one. Um, so a lot of students kind of forget this aspect of Diels-Alder because, again, usually it's something like this. It's very simple, like hindrance or whatever, right? But also don't forget about electron withdrawing groups, increasing reactivity. And actually 14 is kind of the same way, and 14 should be C because again it has the most electron withdrawing groups, right? So same concept. So most reactive diuniphile, yeah. Okay, and why does that happen? Well, think of it as it makes the double bond weaker, making it easier to break, right? So it makes it easier to break. And I think not in this chapter, but the later after the chapter after, I think we're going to be talking more about what electron withdrawing groups do, and we're going to be involved with electron donating groups as well. So things like that, why they're important and what they do to molecules. So we'll see more of that later. But for Diels-Alder, all you have to kind of know is again hindrances, steric hindrances, electron withdrawing groups, things like that. Dienes are uniphiles, right? So, and this is a big Diels-Alder is a big reaction because it's one of those special ones, right? Okay, so next page we have 16, 15. Oh, actually, I think I skipped 15, right? Okay, let's go back to 15. 15. You guys should have gotten D, which of following is least reactive. So again, same concept, and you guys should have gotten D, right? So again, 3 and 4, 1 and 2 we kind of saw on number 12, but 3 and 4, what's the difference between them? 4 is cyclic, right? And 3 is not cyclic, not closed off. Okay? And actually, sorry, this should have been C. And why, even though it's cyclic versus acyclic, what's the difference between 3 and 4? Well, 3, so same concept, right? We want S cis, so this is S cis, and then this is S cis as well, but this one's closed. Um, so what's the difference? What makes these different? So this case, and kind of same thing with chair conformations, this can pucker up, right? Can bend up, um, and it can, yeah, just think of, if you think of it as flat, right? And let's put double bonds here. Okay, I guess that was but the bond can happen on the bottom, right? And then your double bond or your diunified will be right here, right? It can happen in the bottom where it's kind of like a bridge, right? It'll make a bridge. But this one you can't make a bridge because it's you can't rotate these single bonds, right? Because or not single bonds, you can't rotate these bonds because they're on the double bond, and you can't just attack from the back because it's not cyclic and it's not stable enough, right? Because and it'll just again it'll make that weird big bond, right? Because then it'll have to look like this, right? So that's not good. So kind of like that. Sometimes you kind of just visualize it, but yeah, cyclic um, dienes are often, especially compared to their acyclic counterpart like 3 and 4, go with the cyclic. So yeah, that's why 3 is the least reactive because again, it can't make a bridge, right? And you'll see a lot of bridges later too. I think the next example is a bridge. Okay, so let's go with 16 and 17. What kind of a bridge? We kind of make. Okay, well, anyways, again, pause the video, you know, do your thing and see what you can get. So for 16, you guys should have gotten C, only 3, and why is that? So again, another thing to keep in mind with deals, all their besides now that we're getting to the product side of it, right? We've been talking about the reactants, like what they have to deal with, what you need, things like that. So in this case, we're talking about the product. Well, the product states that stereochemistry of the uniphile stays same, stays the same, right? So in this case, the diene is a what? It's cis, right? Cis with the carboxylic acid. So 1 and 2 is showing that they're trans, but 3 is saying that they're cis, right? These groups are cis, so they'll remain cis, right? That's all there is to it. And then same thing with 17, same concept. 17, you guys should have gotten just A, right? Because just because we don't see the hydrogens, just because they don't tell us, oh, they're cis, we know it's cis because from here, I mean, we don't even need to draw the whole molecule, but from here, we know there's hydrogens over here, right? And we know it's in a double bond, so it can't rotate, so, and these are cis as well. So they'll stay cis, which is A, right? 2 and 3 is saying that those H's aren't cis, so that's what you have to look for. Just don't forget about the stereochemistry of the diene, or I mean dienophile, right? Okay, so that was pretty easy, right? Especially with the choices and kind of some things with things like these, you can even take these questions a step further, like what would the dienophile have to look like to get choice 1, 2, 3, right? Or you can even take out the answer choices and try drawing it yourself from scratch and see if you can get the right one. But just different practices like that, especially with these questions. I mean, obviously these questions aren't going to be exactly what's on your test, but there's only so many ways you can ask a question, and we've seen a couple different ways already, and you can even add a couple more, and by the time you experiment, you kind of twist these questions, you pretty much have the question down. You expect the question. So another good strategy, like that's a good strategy. Just test taking strategy, or you know, studying strategy, I guess. Just get the questions mold it, shape it, do whatever you want, and yeah, practice with that. So Now, 18, 19, 20. So take a couple of seconds, or I mean minutes, screenshot, take notes, answer them, and see what you guys got. So, and again, now we have the bridges, and you'll see how they're kind of represented, right? Okay, so 18 is fun one, and you guys should have gone D, or I mean, sorry, 18, you guys should have gone, um, yeah, D. So, this one, why is it D in the first place? So, now we're seeing a triple bond, but, no big deal. So, let's start from scratch, because this is one of those things that's um, a good practice compared to the other ones, because those other ones, the last two were just stereoisomers, so it was whatever, right? But this time, it's not so much about stereoisomer, right? Because it's triple bond and there's no cis or trans. So let's see here, CO2H, CO2H. So what I do, I like my colors, right? So I know, right? We're connecting pretty much this way, right? So I'm gonna do that, and then we're gonna make a bond from this end to this triple bond, right? So I'm gonna do that, and then last but not least, this double bond to over here, right? So our product in the end should look something like this. H, and let me do the colors, right? We did blue, and then we did purple, right? So something like this, right? But obviously our choices are in a, I guess, a more 3D fashion. It made a bridge, things like that. So now, just looking at these, we for sure know that we're going to have this bridge over here, right? And what is this bridge? We have one, two carbons on that bridge, right? So we can eliminate three. We can eliminate choice C because that bridge is missing one carbon, right? It's not triangular, it's square. So now we look at the other one. So for 1 and 2, what are we missing? So 3 is missing bridge. 1 and 2 is missing what? It's missing pi bond, right? It's missing this pi bond. So the only logical answer choice now is 4, is D, right? Because it has the pi bond, the bridge is there, the new bonds are there, and that's great. And also another thing is that even if 1 and 2 did have that pi bond, we know Diels-Alder prefers what? Endo positions, right? Endo positions. And 4 is the only endo position there is. Um, 1 is an endo position, but it has axial, right? And we know axial is not the most stable compared to 4, which has both equatorials, but it's still endo, right? 2 is exo. Um, 2 is exo, so that's definitely not the right one, right? So things like that, endo, and then I'm going to put here equatorial, right? So not too crazy. Um, yeah, endo's the one you're kind of looking for, and then don't forget, the little details like don't forget the double bond. We only used one pi bond, right? When we moved this, we didn't use both of them, right? Okay, so 19. I think 19 I can just fit here. 19, you guys should have gone the longest wavelength. You guys should have gone D, right? And why is that? So for 19, oh sorry, 19 is B. If you caught me, good job. Okay, keeping you guys on your toes today. Okay, so 19 is B, and why is that? So the more stable, so again, stable because it's conjugation, right? Um, the longer wavelength you need, right? The longer wavelength you need. So for UV. So that's it, right? And this kind of deals with kind of the spectroscopy side of things, but other than that, it's um yeah, it's just a good concept knowing that the more stable, the longer the wavelength you absorb, right? So that kind of applies for other things other than UV technically. So okay, and now for 20, you guys should have gone D, right? Because what do we know UV does? And this kind of goes back to spectroscopy again, because we know UV excites electrons, right? So if it excites electrons, it's going to jump from its um, excited states, right? So the only excited stage here that's correct is the pi to excited pi, which is D. Another thing to call that is anti-bonding, and you'll see that actually a little bit later. But I don't know if this in this chapter or the next, but anti-bonding is pretty much the excited state of something, and anti-bonding just denotes with an asterisk. Um, so asterisk equals anti-bonding. Anti-bonding. So A completely jumps up a level, right? Same with well actually B jumps two levels because of it bypassed pi and then went straight to anti-pi, right? And C, same thing. And D is the only one that excites it, right? So that's a good concept. Kind of just there to, don't forget about spectroscopy. Don't forget about the light spectrum because all of these kind of relate to that, and all of these kind of take part into that, right? Conjugation, especially. And that's where you kind of see even kind of see going back into IR, aromatics are always pretty far down because they're all conjugated, right? So, okay. So with that being said, let's move on to our summary. And hopefully this chapter, yeah, well, actually this review touched upon a lot of things that we're going to cover because obviously there's no other extra information. We didn't miss anything, which is good, right? So first things first, conjugation. Let's go to conjugation. So again, you know, when p orbitals, going back to the first few questions we did, when p orbitals overlap and on adjacent atoms, right? And it doesn't always have to be carbons. It doesn't always have to be whatever, right? As long as in adjacent atoms and as long as those p orbitals overlap. And this is kind of how to visualize those p orbitals. So let's say we'll always see this, right? Like the general structure, and this is kind of what they look like with the p orbitals, right? So over here, over here, over here, and these all overlap, right? And that's where the conjugation happens. So just go back and forth, right? So, and these are sp2s, we know because it's um, one electron each, right? And which makes sense over here because these are all sp2s, right? So, okay. So now, we know again conjugation is so similar to resonance, so delocalization. So this just again conjugation is to stabilize, and we know to stabilize equals less energy, which is heat of hydrogenation, whatever, less energy, and chemical shift of carbocations again to resonance, less shielded. And this is now again we talked about spectroscopy, right? So this is kind of like the CNMR. So and we know aromatics de-shield something. De-shield, de-shield, right? And things like that. So conjugation, um, that's pretty much it, right? Nothing too crazy. It's pretty much exactly the same definition as resonance, right? Okay, so now we're still in conjugation, but this time, what are some common examples of what can we conjugate, what can we resonate, right? So these are the common examples. First, we can have the three atom allele system. So you've all seen these examples before, but this is kind of like the more formal, like, okay, this is a three atom allele system. It's definitely going to conjugate, right? And what pretty much this means is that you'll have an atom here, an atom there, three atom allele system, so X, Y, and then Z, and this is going to have some kind of charge, right? And I'm just going to note that as an asterisk, right? And then, and you can see how this resonates, right? So X again, Y, Z, and now who has the double bond? This one, and who has the charge? This one, right? And you can kind of see how it just goes back and forth like that, right? That's the three allele system. And now let's go to, of course, conjugated double bonds, and that's what we've been talking about, right? So the best example, obviously, is the benzene, right? So that's too bad. Three is the cations having a positive adjacent to a lone pair. So cations having a positive um, charge adjacent to lone pairs. So something like this. Let me put these in here so we can kind of separate them. Lone pairs. So something like this. Again, right? And they're gonna just switch. And this one's important because you can see that they're right next to each other, right? So pretty much they're just switching spots. It's not it's different from the three allele system because obviously this has the three atoms, right? And it has a double bond. But instead of a double bond here, we have the lone pair. And we talked about lone pairs earlier, kind of taking that place of a double bond, right? So now it's kind of making sense. It makes sense that lone pairs can jump like that because, I mean, technically they are in a p orbital, they are pi bonds, right? So 4 is the most forgotten one, but it's still relevant. So, and this is the longer title actually. Double bonds have one atom that's more electronegative than the other. So basically, if you have this, and let's say Y is the more electronegative, then that Y is going to take everything, right? So now you have two charges pretty much. So that's what that means. So your Y will have the negative charge and it's a lone pair, right? And that's what it means. This one is the least common one because while it does happen, um, the other three is just a better option. And yeah, things like that. So nothing too crazy, and it's different from here as well because these are just regular lone pairs, while this is an ion, right? It turns into an ion, like anion, I should say, to be more specific. So yeah, that can happen. So keep these in mind. Um, depending on who you're taking the class with, they could go all out, right? Make you find every single thing. So pay attention to things like these. But again, you don't really see it a lot of this because again, if anything, it's just carbon double bonds and oxygen, right? Because you'll never see halogens double bond to anything, so those aren't really gonna affect or isn't gonna apply to this, right? So if anything, you'll see with carbonyl groups. But okay, so now next thing, let's see, resonance hybrid contributions. So how do I want to title this? Resonance hybrid. So one, more bonds and fewer charges. So again, same with resonance, right? More stable. And that's what we talked about with the charge for the other when we were doing the order, right? Two, every atom has an octet, more stable as well, which makes sense because if it has an octet, it's going to be um, again fewer charges, right? Three, negative charge on electronegative atom equals more stable. So that was kind of like the fourth one on our conjugation list, right? So these are just kind of showing the effects of conjugation of resonance. Um, especially when we were ranking things, we kind of talked about the charges, and the oxide is kind of the same as the charges and more bonds, things like that. And then you know, especially with resonance and conjugation, whoever's holding the one that's holding the negative charge obviously has to be the more electronegative one because it's gonna like it better, right? It's gonna not mind it. So things like that. Yeah, that's pretty much it with resonance hybrids, right? So now let's move on to conjugated dienes. And obviously, the way I'm summarizing this to you is kind of the way I feel like the class focused on, and the more high yield, the more, I guess, more common ones. So feel free to, you know, do your own or use mine as a template and then add on little things like that, or made them more elaborate, made them more detailed, I guess. But this is a should be a good kind of like if you were taking the test, a good refresher and or even to find out a good refresher, a good summary of what you should know. So conjugated dienes, aka 1,3-dienes. Right. First, we know the easy, right? Cis, trans, whatever. And we were also introduced with S cis and S trans, right? And with that, we basically, this is the S part, right? This is the S part. So right now, this is S trans, but we can rotate it to make it S cis, right? So S trans, S cis, right? So it's all about this over here, so we can rotate that wherever. Okay, so now we have here more kind of criteria, more description. So in conjugated ions, CC single bonds are short. So that's because of the S character. So the higher S character, the shorter the bond length, right? So for two, it's more stable than similar dienes that are isolated. Obviously, right? Because there's no conjugation happening, there's no resonance, there's nothing. So three, some reactions are different from isolated dienes. So, and these all make sense because, again, with conjugation, we get the 1,2, 1,4 type thing, right? So, though isolated dienes don't get that. So, that's good. That makes sense. And then fourth one, absorb longer wavelengths of UV. Again, because of the resonance, because of the conjugation, because of the stability, right? So those are the things you kind of want to look out for. Those are kind of the effects of conjugated dienes, which is good. Okay, so now let's move on to our electrophilic addition. So electrophilic addition, obviously we did some of that, the 1,2, 1,4. So let's kind of just go through this real quick because there's not really a lot of explaining. Um, but for isolated, this is the one that we keep talking about, the last page. One product, and it follows Mark's rule, right? Markovnikov. Conjugated. Conjugated, we know two products and either 1,2 or 1,4, right? Addition. So now we get to talk about 1,2 and 1,4 addition. And obviously these are nucleophilic attack, right? And again, we know 1,2 is the kinetic, and obviously it's fast and low temp and less stable. So less stable and fast. And if you actually, let's do an energy diagram later. 1,4, again, thermo, slow, high temp, more stable. So if you were to see something like this, mm, let me add this, predominates at equilibrium. So something like this, which one do you think is which? So 1, 2, you should get the this one, right? And 1, 4 is this one, right? Because 1, 2 is the um, fastest one. So that means now you got to think about the activation energy. The lower the activation energy, the faster, things like that. And you can kind of also see how it's less stable because of that lower energy, right? So that's kind of what you have to think about when you compare these two in a graph form. But you guys won't really have to know that as long as you know this, right? So that's pretty much it. Um, I was kind of trying to reach there, but that's all there is to it. Again, I guess with 1, 2, and 1, 4, also take into account proximity effect, right? Because of that proximity effect, 1 and 4 are obviously farther apart than 1 and 2, so that's why it's more stable. And also, greater stability, things like that. So again, a lot of hindrances, a lot of um, steric type thing, but mostly it's because of like negativity, things like that. Yeah. Okay. Okay. So now that's that. These are good. So now let's go to deals order. So like this is the big deal reaction for this chapter. Um, deals order reaction. So what I like doing with this is that we have a simple. Oh, this is kind of ugly, but right. Oh, okay. And we know it'll connect here, connect there, here, right? No big deal. Um, okay, that kind of turned out bad, but and you just need heat, and you're good, right? So that's all, pretty much the gist of it. But let's see. Now let's list all the things you guys need to think about. Diene can only react when S cis. Electron withdrawing groups increase reaction rate, right? We talked about that earlier. 3, well, we talked about all of these earlier actually. Stereochemistry of dienophile is kept, right? So 4, endo orientation is preferred. And endo orientation is why? Because allows more interaction between electron-rich sites. Sites. So let me draw an endo here. Let's see. So endo, right? And let's do like X or whatever. So what this is talking about, what endo is talking about, and let me label this so you guys don't get lost. This electron rich, right, can interact with these electron rich, right, electron rich sites. So it's more stable that way, it's more favorable that way because you can see that they like to interact, and it's the natural kind of bend to it, if that means anything, right? This kind of natural bend to it, and yeah, that's all I could think of really, but it allows more interaction between the electronegative sides. We know this is electronegative. We know these are electronegative. Or actually, it doesn't even have to be electronegative. But the important thing is you want these, whatever these are. These can be methyl groups. These can be alkyl groups, right? This can be carboxylic acids, whatever. You always want to face them the same way this double bond that we made, right? This is the new double bond where this one is facing. So, and obviously we want it equatorial, right? Because it's the most stable. So, yeah. So now, just more stuff to it. I'm just gonna mention this because this was on my MCAT, and it's like, what? I totally forgot about it. Well, actually, I had no clue what it was. But so dimerization. So this is just fun fact. So dimerization 1,3 cyclopentadiene can dimerize on itself. So what does the pentadiene look like? Can dimerize on itself because why? Because it can act as a diene and a dienophile, right? So and you make this. Okay, right. So you make something like that. And dimerization is pretty much reaction with the same molecule. Same molecule. And that's pretty cool. Now I'll never forget that forever because it was on my MCAT. I don't know why I remembered that. Well, actually, I think I did because I took a while because it was like a question. I'm not even allowed to talk about the MCAT questions, but I went to this to AAMC. It was pretty much asking like, what reactions do this whatever you know go through, and dimerization was the answer choices along with like oxidation, reduction, things like that. So I don't know if that was the answer or not, but I just remember that because that was the thing. Like, what is dimerization? So now you know. Hopefully, if you see that on your test or whatever, you won't forget it. Because honestly, again, I'm pretty sure a lot of you guys are aiming for like grad school, professional school, things like that. Those tests are just random, right? They're just random. You never know what you're gonna get. But you know, OChem is one of those classes that's like in everything, and it involves the biochem, it involves kind of gen chem, it involves gen bio, which is pretty much all the professional school, all the sciences you'll ever need to know, right? But I digress. Anyways, now our last part is the UV light absorption, and we know that pretty much the more conjugated, the longer the wavelength, right? The longer the wavelength you absorb. So let's see, energy here, and this is kind of what it looks like. So these are our where I was talking about the excited state, right? So we have our orbitals here, and then we go through the UV or the wavelength. We get it, we absorb it, right? And then it jumps up like this, right? So nothing too crazy. Um, and again, this goes into like a little bit of physics. Oh, and OChem goes into physics too, right? Um, Pretty much it protonates it to a higher level, right? And that's pretty much it. That's pretty much it with that. Again, shorter wavelengths are obviously higher frequency, blah blah blah, right? But it's just extra information that you may or may not need, but it's fun to know, especially if your professor tries to kind of sneak it in there, you'll know. Okay, so with that being said, that's all I have for you guys. This is probably one of the more important chapters because again, conjugation pretty much sets the stage for the next few chapters with the hermeticity, things like that. So hopefully I see you guys back again. Um, and hopefully this was helpful. Hopefully you guys take the questions, take them, please, practice them, share them with your friends. Tell them to watch the videos, tell them to watch the explanations. They'll always be here recorded, right? And yeah, I hope you guys like that video and see you again next time. Bye.